What kind? Any. Are there mirror planes? Yes. What kind? How many sigma V's? Infinite. And how many sigma H's? Just one. Okay? So here we go. Infinite number of sigma V's, just like in the case of CO, right? And then one sigma H, right, that bisects the OO bond and reflects both oxygen atoms. Okay? So there we go. Now, this one's the best. First, this molecule is called diborane. Okay. What are the weird things about this molecule that you're already uncomfortable with? 2 bonds of hydrogen, right? What's that? This is a real molecule. Hydrogen group. Yeah. Well, welcome to the real world. We're going to show you how this works. This is called 3-center 2-electron bonding. This happens a lot in inorganic chemistry. Okay? Even though I've drawn 2 lines to that hydrogen, right? As we'll see later on in this class, that doesn't mean that there are 2 localized bonds. What this means is that there is, right, a hydrogen here, and it's basically symmetrically located between those 2 borons. Okay? The bond distances from this boron to this apical hydrogen and this boron to this apical hydrogen are identical. But there are not 4 electrons there. There's actually only 2 electrons in that interaction, but it's a molecular orbital that contains both borons and that hydrogen. 2 electrons, 1 orbital, 3 atoms. That's the essence of molecular orbital theory. Okay? We'll get to that, but right now, we need to understand the symmetry properties of this molecule to even go forward. Yeah?
Oh, I was going to ask, how does that affect the bond strength, but I figured you might get to that later, is what it seemed like.
Yeah, let's defer that more complicated. Okay, what's the primary axis of rotation, and where is it? C2, where is it? I heard more than one. I see this, I see this. I'm missing one. This. Okay? There's actually 3. Okay? And they're all C2. And so is there another primary axis of rotation? Is there a higher order axis of rotation than a C2? Is there a C3? C4? No. 3 C2s, and that's it. So which one's the highest? They're all equal. Okay. So now, where are the mirror planes? Are there mirror planes? There's clearly mirror planes. Where are they?
Bisecting the wedge dash hydrogen throughout the plane of the molecule.
Right, so bisecting, so there's a mirror plane here. Right? Is there another one?
One that falls parallel between 2 bridge hydrogens.
Let's see this, okay? And then there's another one. That's right. So basically, there are mirror planes coincident with every C2, but at the same time, they're what? Perpendicular to another C2. Okay? This is a special case. It's the best one. Okay? Where everything's equivalent. In a situation like this, where there's only a few examples, and you're going to be able to recognize them right away, because you're going to see, oh, C2, there's a few of them, they're all the primary. They're all essentially equivalent, right? Mirror planes, well, they include all the C2s and they bisect all the others, okay? That's a special circumstance that will be very easy for you to identify quickly, okay? So in this particular special case, 3 perpendicular C2 axes, they're all primary, therefore we're just sigma, no V, no H, because it's both V and H at any one time. Okay? When you can't make a decision, what do? You just ignore the situation. Okay, so that's it. Those are mirror planes. So inversion centers, pretty easy. Okay, I think we could all see inversion centers. We're pretty used to that, having taken math since we're like 10 years old. What's important about inversion center, right? It's a center or a point. Okay, so we talked about the genesis already. We talked about a plane. This is going to be a point of symmetry. Okay, it's pretty easy to look at it, right? Just then in Cartesian space, where the inversion center will be located where? Yeah, just at the origin here. And we know that inversion really has to keep all aspects of the object identical. So this triangle over here, right, which is in the positive xy plane, let's say, right, is pointed down, okay? Right, and we invert, right, to the negative xy plane, or negative xy quadrant, excuse me, then that is pointed now up, okay? Point to point, okay? There we go. So, what's important to realize, right, about an inversion center is that it's a composite symmetry element. Now we're going to start to talk, the next two, inversion center plus improper axis of rotation, are composite symmetry elements. They are the summation of two other symmetry elements. And so you can essentially equate inversion center, which we're going to give the symbol I, as a C2 and a sigma H. What does that mean? You're going to do a sequential, right, series of operations. So now we're going to start to get into operations. Where basically, if there's a C2 axis at the origin that comes in and out of the board, right, we're going to do a C2, right, rotate 180 degrees, and then what are we going to do? What's the sigma H part? We're going to reflect in a plane perpendicular to that C2. So remember, the C2 comes out here, so where's the mirror plane, the sigma H? It's here, right? And so if this is a flat triangle, which it is, right, we do a 180-degree rotation, and then we just reflect the object into itself, right? That is equivalent of doing an inversion operation, an inversion center. So C2 plus sigma H is inversion, okay? Or it's just reflecting across through the origin, okay? So let's orient. This will be simple. Ready? Everybody ready? Okay. Ethylene, or ethene. Is there an inversion center? Okay, I see a lot of A's. Okay, where is it? Yeah, okay, pretty simple, right? Midpoint of the double bond, H goes into H, C goes into C, so on and so forth. No problem. Okay, methane. So methane, what's the geometry of the molecule? Here is tetrahedral, okay? Now, symmetrically, in terms of symmetry, it's also what? Tetrahedral, right? Because it has 4 of the exact same peripheral atoms bound to the central atom in the corners of a regular tetrahedron, meaning they're all spaced how many degrees away from each other? 109 point, whatever. Yeah.